Thank you, Martha, for your very nice introduction. I am Cristina Man, Assistant Professor at Department of Biomedical Engineering of the Hong Kong Polytechnic University. So today I will introduce some of our previous work on developing and also applying some smart wearable systems with real-time feedback to improve the human balance and walking ability. So to start, maybe I can briefly introduce myself. So I am originally a prosthetist and orthotist, and I completed my undergraduate study and also the internship at the Sichuan University back in 2008 and 2012. So after my undergraduate study, I am working as a certified prosthetist and orthotist at the China Rehabilitation Research Center before I come to PolyU for my PhD study, in the middle of which I have been to the University of Michigan as a visiting research scholar. Okay. So after my PhD graduation, I went to Sweden as a lecturer, later assistant professor at Jönköping University from 2018 to 2020. And then in 2020, I came back at PolyU as an assistant professor. So this is a very brief introduction of myself. For my research, the reason why I'm specifically interested in dealing with the human balance and also the walking ability is because the falls have been a very major public problems. Okay, so So the consequence of falls can be very significant, including the severe physical, psychological trauma, enormous medical expense, and also sometimes even high rate of mortality. So this is why we're interested in dealing with falls. And because of the rapid aging in Hong Kong and also the other regions over the world, the death and also hospitalization due to falls have also been increased over the past 1 to 2 decades. And here is the statistics from Hong Kong. So to handle the fall cases, usually we have some fall prevention clinics and also some screening programs where after a person fails, we can have geriatrician doctors to introduce or transfer the older people and also some patients for some necessary treatments and also medications that are dealing with falls. But these approaches have been prevent after falls. So if we want to prevent before falls, we could have some balance trainings that can improve the balance and reduce the risk of falls. And these figures shows the normal or the general clinical practice that how we can train the balance of patients. So the first approach is to have some physical or rehabilitation therapists to have some face-to-face trainings for the patients. And for this approach, it demands a huge amount of manpower of healthcare professionals, which has been rather lacking in Hong Kong and China. And then we could also have some assistive devices to help do the trainings for the patients and also to assist the rehabilitation therapists. But for the existing or the previous approaches, they have been the cumbersome devices, which means the older people and also the patients need to go to rehabilitation centers or clinics to do the training, and which can be very inconvenient for this group of patients. So this is why we were wondering whether we could have some wearable approaches to assist them. Okay, so for this figure, it generally shows the consequence, the risk factors of falls, and among them, the balance and gait disorder has been the second leading cause of the falls. Okay, and if we have the proprioceptive, visual, or vestibular sensory deficits, we would also the patients would also have some sort of deficits in balance and gait. And among the proprioceptive sensation, actually the foot tactile sensation is one key element because during standing, during walking, during transferring tasks, our foot will always be in touch with the ground to continuously collect the information of the supporting surface, which is again very important for our sensory input and also the maintenance of balance. So previous studies have also found that the reduced for tactile sensation will reduce our sensory functions, lead to balance and gait disorders, and increase the risk of fall. So this is why our hypothesis was whether we can improve the foot tactile sensation to improve the balance and gait and thus reduce the risk of falls. So we have conducted a series of studies and evaluate the developed wearable feedback devices effect in the steady standing with perturbation, and also during walking of different populations. And I will introduce them one by one. So in general, we have developed a series of these what we call as smart wearable devices or smart insult systems, and apply them in the older adults, in young adults, in some patients with stroke, and to evaluate its effects on the steady postural balance with some perturbations during walking, etc. And I will also briefly introduce some of our ongoing work in this field. So our very first study was conducted in 2013, and we were focused on the steady posture stability. So for this figure, it shows an older people who is standing in the Roomberg position, which means his feet are put together, and then his eyes are closed, but now it's covered, and with his arms crossed and rested on the opposite side of shoulders. So the Roomberg test or Roomberg position is a very common test that we use in clinical practice to evaluate the balance performance of a person. And when the person is standing in this position, we can evaluate the posture sway or the how much the posture has been moving during the Roomberg test. So one way to evaluate the balance is to look at the area of the center of pressure during the standing. Okay. So this is the very first prototype that we have developed, and we have put the 3 force sensors at the each of the left and also the right feet to capture the plantar force during walking, during standing, sorry. And then we can imagine, so during standing, if our posture move forward, then the force or the capture at the plantar surface of the forefoot will be increased. And then if our body move to the left side, then the force capture at the left face metatarsal head will also be increased. So this is some general ideas about how we determine the posture sway area. So whenever the posture sway to the anterior, posterior, left, or the right side is larger than a threshold, then the vibrators that are located at the anterior or the front, the back, the left and right side of our upper trunk will be activated to remind the users to move their body in the opposite direction. So this is a very simple way of how we use the vibrotactile to provide the feedback or alarms to the users. And for this figure, it shows the changes in the speed area of our center of pressure of the healthy young and older participants. So for the left side, this is a condition where the system was turned off, which means we were not providing any feedback to the users. And the right one is the condition where the system was turned on, or in other words, the young and older users can receive the vibrotactile feedback. And we can see that the sway area of the center of pressure has significantly reduced after turning on the system, which indicates the improvement of the static posture stability. But we all know that actually most happens do not happen in this static standing position. So most falls are actually happening in the dynamic situation. So for the second study, we are thinking how we can further optimize this system to tackle more challenging tasks. So for the second study, we have developed a moving platform. So this is actually a moving floor that can suddenly move forward, backward to the left, and also to the right of the side of the users. Okay, so as we can see, um, for this kind of setup, it actually simulates the condition when a person is standing in a bus, in a train, in an MTR or ship that suddenly accelerate and also decelerate. And we would like to evaluate the effect of the system. So for this system, we have further optimized or simplified this device by reducing the number of force sensors. So in this second prototype, we only put four sensors at the first metatarsal heads and also the heels of the left and right side. And by looking at the plantar force captured at the left and right first metatarsal heads, we will be able to understand the movement to the right side. And then by looking at the force sensors or the forces captured at the first metatarsal head and also the heels of the left foot, we will be able to understand the posture sway to the left side. So this will also work for the right and also the posterior or backward posture sways. Okay. So for this figure, it shows the results. We can imagine if this moving platform suddenly move forward, our body will actually and relatively move backward due to the inertia and reach a maximal posture sway displacement, which we define as S max 1 over here. And after reaching the maximal posture displacement, our body will start to react to these Sunday perturbations and then to move forward. And eventually, our body will move in the same speed with the moving platform and reaching a new posture equilibrium. So which we, for the position where the of maintaining or reaching the new posture equilibrium, we have defined it as S max 2. Okay, and the time between the start of the moving platform as well as the time of reaching the S max 1, we refer to it as TP, which is the reaction time in this case. So which means upon reaching S max 1, our body will, it takes this time, the time that reaching the S max 1 is the time where our body can react to this perturbation, okay? And then the time between S max 1 and S max 2 are determined as T recovery, which is the recovery time of our body when receiving this kind of balance perturbations. Okay, so for this figure, the red line indicates the situation where the system was turned on, and then the blue line indicates the figure indicates the condition where the system was not turned on or turned off. Okay, and by looking or by doing some statistical analysis, we were able to find that upon turning on the device, the displacement of our center of mass has significantly reduced for more than 10% after only one training sections. Okay, and this happens in all the forward, backward, left, and right directions. And also we were happy to find that the reaction time to this balance perturbation has also significantly reduced upon turning on the device. So this indicates that by using these wearable insole systems, we were able to improve the reaction time and also reduce this posture displacement in response to the balance perturbations in four directions. Okay. So for the first two studies, we are mainly dealing with the standing positions, and then for the second study, we would like to see whether we can deal with the walking conditions. And by this time, I'm most interested in the patients or patients with stroke in this scenario because I'm a PNO and I have been working with the patients with stroke a lot during my clinical practice. So for the patient with stroke, because of this impairment, we can say that usually their affected or paralytic foot will have this inverted foot posture or position. And with this abnormal posture, usually the plantar force at the lateral side of our foot will be significantly larger than the medial side. And this will cause some tissue damage or injuries with this abnormal walking and standing patterns. And in the long term, if the patients kept walking in this abnormal postural position, this deformity will also become fixed or unable to correct with the external forces. So in this case, the patients will need to go for surgeries to correct these abnormal positions. Okay, so that is why for our third study, we have further simplified the insole system by putting only two force sensors at the medial and also the lateral side of the forefoot of the affected side of patients with stroke. So whenever the medial forefoot the plantar force captured at the medial forefoot is 25% than the lateral side of the affected forefoot. A vibrator that is located at the wrist will be activated to remind the patients with stroke to put more pressure at the medial side during walk-ins. And this figure shows the very simple prototype of that device that we used. Okay, and we have used some intraplantar pressure measurement system to evaluate the changes in the medial and lateral forefoot, medial and lateral midfoot, as well as the medial and lateral rear foot of the patients with stroke during walking. So for this figure, these dashed lines, it indicates the condition that the patient is walking without turning on the system, and then the solid lines indicates the condition of turning on the system. Okay, and for the gray lines, it indicates the condition of the unaffected side or the healthy side, and then the black lines indicates the condition of the affected side or the paralytic side. So if we look at the black and also the gray dashed lines, we can see that before turning on the system, the plantar pressure of the medial forefoot of the affected side is significantly smaller than that of the unaffected side, which means our patient needs to rely more on their unaffected or healthy side during walk-ins. And after turning on the system, the plantar force captured at the medial forefoot has significantly increased. Okay, and then the difference between the affected side and also the unaffected side has also been smaller, or is actually comparable to each other after using the device for only one training section. So this also can be identified when we look at the plantar force of the medial midfoot. So we were also very happy to see that the difference of the affected side and also the unaffected side has been significantly reduced, which indicate that the plantar force or plantar pressure loading has been improved after using this system. Okay. And we were also interested to see the underlying mechanism of how the stroke patients change their lower limb movement to achieve this improved plantar foot loading. So this is why we have also used the three-dimensional motion capture system to capture the angles changes of the hip, knee, and also the foot during walk-ins. So again, we were able to see that this abnormal foot inversion of the affected side has been relieved after using this system, and the difference between the affected side and also the unaffected side has been significantly reduced. Okay, we were also happy to see that. So the compensation of the healthy side or the unaffected side has been reduced. So as I mentioned, because the stroke patients have this abnormal foot position, they need to rely on their unaffected side or the healthy side to compensate for the deformity of the affected side. So that is why if we look at the unaffected side, usually the knee flexion angle is significantly larger than the unaffected side. And also the hip abduction angle would be significantly larger than the unaffected side. And we were able to say that by using this system, the excessive knee flexion and also the excessive hip abduction angle has been reduced, which means that the compensation at the unaffected side has also been reduced. So this further support that this device can not only improve the plantar foot loading, but also improve the walking ability and also the excessive compensation at the unaffected side for the stroke patients. Okay. So for the previous three studies, we were mainly using the force sensors to capture the plantar force of the different populations. So we'll wonder whether we can also use the some sensors to capture the angles during walk-ins. Because during walk-ins, if it's stand space, our foot will be touching the ground, and we will be able to capture the plantar force information. But during the swing phase, which means our foot is not touching the ground, we will not be able to measure the plantar force information. So for the second study, we have used some inertial motion sensors, which are accelerometers, gyroscopes, and also magnetometers to measure the angular parameters during walk-ins. We were also able to find that during walking, if the foot floor contact angle is larger than 20 degrees during walking, actually there will be higher chance of slips among different populations. So for this second study, we use the IMUs, or inertial measurement units, to measure the foot floor contact angle of the dominant side during walking. Okay, and then we also don't want the foot floor contact angle to be too small, because if it's too small, then there will be higher chance of trips. So we have determined or precise a desirable range of foot floor contact angle of between 10 to 20 degrees. So whenever the foot floor contact angle is larger than 20 degrees, a high tone will be provided to the users to remind them to reduce the foot floor contact angle. And when this angle is smaller than 10 degrees, low tone or auditory feedback will be provided to the users to adjust their gait patterns. So this chart shows the overall setup of the system. Okay, and we have only put the two IMUs at the dominant and also the non-dominant foot during walking. And for this figure, for each dot, it shows the foot floor contact angle of each step during walking. And for the first condition, this is the baseline walking, which means the patient or the user, they just walk in their natural ways without any interventions. And for the second condition, this is the condition where we have a verbal instruction, which mimics the condition that a physical therapist is introducing or instructing the users or the patient to do gait trainings in clinical settings, and followed by 4 training conditions, which means the this feedback system was turned on and the feedback was provided to the participants during the work training. We were also interested in whether the outcomes of the device can carry over to or can last for a while. So this is why we also have a post-training condition where the device was turned off and then the patient or the participant just walk on the treadmill for 2 minutes. So as you can see, so when we have this verbal instruction, there is a tendency that the foot floor contact angle will be controlled, but it's actually the effect was not quite good. That is because just based on our eyes, actually it's very difficult for us to determine whether the foot floor contact angle is within the range of between 10 to 20 degrees. And it is also difficult for the participants to feel the location or the angle of their foot during walking just based on their own foot tactile sensation. So we can say that for the two conditions, the changes in the foot floor contact angle was not quite large. And then during the 4 training conditions, there is a tendency that the foot floor contact angle will be moved, will be reduced, and then increased amount or percentage of the foot floor contact angle will be within this desirable range. And we were also happy to say that even during the post-training conditions where we have turned off the system, these positive effects actually pretend or carry over to the post-training sessions. So this again indicates that firstly, by using this very simple biofeedback system, we were able to retrain the user's gait pattern and improve the foot floor contact angle. So hopefully this angle can also be used to reduce the risk of slips during walking, and more efforts are needed in the future. Okay, so again, we have also used the 3 motion capture system to study the underlying mechanism of the adaptations by using this kind of feedback system. And we will identify that there are some differences in the coupling ankle variety of the hip, knee, and foot joints, which means the joint coordination has also been different upon using this kind of wearable system, which may partially explain the changes in the foot floor contact angle during walkings. And due to the time, I will not go into details. So in summary, these 4 studies have supported that by supplementing or augmenting our foot sensory input, we will be able to improve the balance and also the gait control of the young and older adults, as well as some patients with stroke, which can potentially reduce the risk of falls. Okay, And because with this wearable design, we will also be able to implement these repetitive targeted gait trainings and motor control in both the indoor and outdoor environments. So where the healthcare professionals will be able to evaluate or to assess the training outcomes and process of the patients in a remote settings. Okay? So all these efforts were based on our research, right? We review the papers, we based on our clinical experience to have this kind of ideas. But how our users, like the older people and also the stroke patients, what are their perceptions of this kind of systems? What are the perceptions of their caregivers and also some healthcare professionals remains unclear. So we have also, so to address this need, we have also put some efforts on the knowledge transfer. So we have conducted around 260 interviews and questionnaires among the older people, stroke patients, their caregivers, and also some rehabilitation therapists, as well as the distribution channels of assistive technology products in Hong Kong and also mainland China. And we will identify that there is actually a huge amount demands of this kind of devices. And of course, further optimizations are needed. Okay, so this is why we have further modified or optimized the device. So as I introduced, we have been able to verify or validate that both the force sensors and also the MUs or motion sensors are capable of evaluate and also capture our standing and also walking balance and gait patterns. So for the ongoing work or in the latest prototype, we have integrated both the force sensors and also the MUs of the left and also the right foot. And we have developed applications that can be installed on smartphones or tablets to visualize the gait patterns. Okay, and this is how the device looks like when older people is wearing this device. Okay, and with the smartphones, we can capture those data and upload the data to the cloud. So we will expect that by capturing a large amount of data, we will be able to have some big data analytics and to recognize the individualized pattern of different individuals to provide some customized or individualized feedback to each of the users in the future. So this is the overall setup of the system. Okay, and this is the user interface of the system. Okay, so for this figure, this is actually very interesting. So it was back in 2019 where I was still in Sweden, and my colleagues were using this system to capture some data in Hong Kong. And you can see that even with this 6 hours of time difference, I was able to visualize the information in the real time, and the pattern was similar or identical to the pattern that my colleagues in Hong Kong were captured. So by that time, I was, kind of joking that maybe in the future we can provide the therapists with the option of the working from a distance. But at that time, it was only a joking, and then all of us are now aware of the story that because of the COVID, our patients with disabilities are actually instructed or recommended to stay at their home as much as possible and avoid to go to some high-risk environments or areas of hospitals where this kind of teletraining or community-based or home-based rehabilitation trainings are actually in need. So we hope that we can continue our previous efforts to make sure that our patients can actually do some trainings in their home-based or community-based environment, and our healthcare professionals can access their training outcomes or process remotely. Okay. So in summary, due to the limit of time, I will not go into details. So in summary, we have conducted a series of studies, and we have validated by using some simple force sensors and also MUs and looking at the foot motion, we will be able to develop some smart wearable devices that can improve the steady posture stability, improve the posture balance under perturbation, improve the plantar force loading, and also walking ability of the young and older adults, as well as some patients during walk-ins. Okay, we will also expect that with the advancement of the big data analytics and also the wearable technologies, we can further develop and provide the individualized feedback to the users to facilitate or promote the implementation of the community or home-based rehabilitation trainings of our patients. Okay, so our ultimate goal is to improve the quality of life of different populations. Okay, so thank you for the invitation for speaking in this workshop. And this will be the end of my presentation. I will be very happy to answer any questions from the audience. Thank you.